Okay, so now that we have seen the Earth's very early history, we're going to go over the main layers, and those are going to be both in the chemical subdivision that we split them up as well as the physical subdivision that we have as geologists for the Earth's interior layers. Okay, so this is one of the key parts of this chapter, and you'll definitely be tested on it many times. Okay, so the three main layers, again, this is based on the chemical components, are the core, which is the innermost part, the mantle, and then the crust, which is the outermost part of the Earth. But there are also physical properties that make us subdivide the interior of the Earth into layers which possess different physical characteristics, such as checking if they are liquid or solid, for example, even though they may be the same chemical composition. So that separates them physically. Or how weak or strong a layer is relative to the next layer. Those makes them different in the physical subdivision, but not necessarily in the chemical one. So the physical subdivisions that we have are going to be the inner core, the outer core, the lower mantle, and the upper mantle, and then later on, I guess, the crust really high up the top, but that's kind of a funky way in which we divide things, and you'll see it later on. So the upper mantle itself includes the transition zone, the asthenosphere, and then the lithosphere. So the lithosphere, which is the uppermost physical layer, is composed out of mostly mantle at the bottom of it in terms of chemical subdivision, and then the top part of the lithosphere is crust if you're thinking of the chemical subdivision. So it's kind of funny how that plays into mind, but you'll see another image later on that will help you clarify that in your mind, as well as your book. Your book has a very good image for that. So again, the innermost part, which is the core, is composed of an iron and nickel alloy with minor amounts of oxygen, silicon, and sulfur. So all of these elements that I just mentioned, oxygen, silicon, and sulfur, are typically elements that form compounds with iron, and that's why we find them there at the core. The density of the core is about 11 grams per centimeter cubed. And again, as a comparison to all of the densities that I will be talking about in the next few slides, the density of water is 1 gram per centimeter cubed. So again, the core's density is 11 grams per centimeter cubed. So much, much, much denser. The next layer after the inner core, is going to be the physical subdivision that has the innermost part of the layer of the core itself within the Earth's interior. So the inner core has the same chemical composition as the outer core, but the inner core is solid, and it has a radius of about 1,216 kilometers. Okay, so that's the radius, and it's a radius because it's a sphere. It's not like a thickness layer. It's a sphere itself because it's the innermost part. So the temperatures here are going to be incredibly high in the inner core, higher than the iron melting point, in fact, but because of the immense pressures that act upon the inner core, the sphere is actually solid, which is what makes it differ from the outer core. That the pressures are not as high as to have a high effect on it. So the iron melting point being so high makes it be liquid in the outer core, no longer having those very, very intense pressures. Okay, so again, as I had said, the outer core has the same chemical composition as the inner core, so it is still mostly iron and nickel. But because the pressures are slightly less than those imposed on the inner core, the outer core actually is liquid. So the iron melting point makes the iron be truly liquid without those immense pressures. The thickness of the outer core is about 2,270 kilometers in thickness, and again, it's just right next to the inner core. So it's the next layer over if you're looking outwards into the atmosphere of the planet. Something that I think is very cool about the outer core is that the is that the movement of the metallic iron within this zone is what generates the Earth's magnetic field. Okay? So I know it doesn't say it right there, but you might be tested on it. So again, something very cool about the outer core is that the movement of the metallic iron that is within it is, within the zone, this outer core, is what really generates the Earth's magnetic field. Okay. The third layer that we have is going to be the mantle. Again, that's the third layer if you're looking at it from the physical subdivision, but only the second one if you're looking at it from the chemical subdivision. And if you're looking at it from the physical subdivision, it's also separated into many. So the Earth's mantle itself makes up more than 82% of the Earth's volume. It is solid, and it's like a solid rocky shell that extends to a depth of about 2,900 kilometers. And it's very distinct in composition from the Earth's crust. Okay, the lower mantle, which again is a physical subdivision layer, is solid, and it goes from depths of 660 kilometers to depths of 2,900 kilometers. Okay, and it is capable of extremely gradual flow due to the high temperatures that it experiences. So although it is solid, you can see you see flow of rocks, the rocks that are a little bit more buoyant, less dense. They do rise up towards the crust, but they do so at a very, very slow rate. Okay, so I said the mantle extended over 2,900 kilometers, the lower mantle being from 2,900 to 660 kilometers depth. Above the lower mantle, we have the upper mantle. So the upper mantle extends from the mantle and crust boundary until about, again, 660 kilometers depth. The transition zone is the bottommost part of the upper mantle, and it extends from 660 kilometers depth to about 410 kilometers depth. At its top, we see a sudden change in density from 3.5 to 3.7 grams per centimeter cubed. So that is what makes it change from the transition zone to the asthenosphere. So the asthenosphere lies from the bottom of the lithosphere, and you can see that in this image. So the asthenosphere lies from the bottom of the lithosphere all the way down towards the transition zone. So it makes it about 310 kilometers in thickness. So give or take a few tens of kilometers, depending on where you are. The asthenosphere itself is a more gooey and weak layer than the rest of the mantle or the crust layer. So it's a more gooey, I would describe it as kind of gooey, where things are able to flow more freely. Not quite liquid though, it's kind of like Play-Doh, if you would sort of imagine that in a way. So with partial melting in some of the portions of the asthenosphere near that boundary with the lithosphere, that's what we're getting in that layer. So because of that partial melting, it allows for a slight detachment, if you would, between the asthenosphere and the lithosphere, which is what causes the lithosphere to travel in a way freely on top of the asthenosphere. So you'll see as we cover next chapter that the lithosphere is where the lithospheric plates are, and those lithospheric plates bounce towards, away, and slide past each other as they are kind of floating, again, traveling freely in a way on top of this gooey kind of subsurface beneath them. Okay, so again, astheno means weak. So asthenosphere is that weak kind of gooey layer. The lithosphere, which is solid, it is made out of rock for the most part. Litho meaning stone, is rigid, and it travels on top of this asthenosphere. Okay, so the lithosphere is, again, as I said, mostly solid rock. And is the uppermost portion of the Earth. If you look at it from the chemical subdivision perspective, the lithosphere is composed out of mantle towards the bottom and then out of crust towards the top. And again, based on physical subdivisions, it's just the lithosphere. So the lithosphere's depth, or thickness, I should say, varies depending on whether it's composed out of continental or oceanic crust towards the top. In areas where it's made out of continental crust is going to be thicker, and in areas where it's made out of oceanic crust is going to be thinner. So as an average, the lithosphere has a thickness of about 100 kilometers, but it may reach up to 250 kilometers under some of the oldest portions of the continents. Okay, so again, looking at the chemical subdivision of the uppermost parts or layers of the Earth's interior, we have the crust, and the crust is subdivided into two, the continental crust and the oceanic crust. So the continental crust tends to be much thicker than the oceanic crust, and it tends to be less dense, more buoyant. So it always tends to float, if you would, on top of oceanic crust when these two meet. So they have fairly different chemical compositions, which is what makes them one denser than the other. So the continental crust averages about 35 kilometers in thickness, and the oceanic one averages only about 6 kilometers in thickness or so. Here is a summary slide of the different layers of the Earth that I just mentioned. The main three chemical subdivisions and the other physical subdivisions as well, made with with each of them with their average thickness for each layer. So I'm not going to test you on the specific thicknesses of them, but I may test you on the order of them and on placing them accordingly to relative to one another. Okay, in fact, you will be tested on this. All right, so this is really mostly just for your benefit. I'll put this slide up along with all the other ones, but if you want to take a little bit longer and pause the video to look at it, I'd welcome you to do so, so that way you get an idea of how they sit relative to one another. So again, if you were to look at the inner core and outer core, again, in the chemical subdivision, it just is the core, okay? And then for lower mantle and most of the upper mantle is just mantle, and then just the really top part of it is going to be the crust if you're looking at it from the chemical subdivisions. From the physical subdivisions, again, you have inner core, outer core, lower mantle, upper mantle, which is itself subdivided into transition zone, asthenosphere, and lithosphere, and then that lithospheric part, again, remember, it contains either continental or oceanic crust.